Welcome, everyone. We'll try to get started on time. Welcome to our third seminar of the semester. For those who don't know me, my name is Mike Celia. I'm director of the Princeton Environmental Institute, and we're happy to present this faculty seminar series. I'll remind you that we have one more seminar for the semester. That will be next month, the first Tuesday, with Denise Mazzarella in the lecture. I'll also remind you that we have a class in here immediately after this lecture, starting at 1:30, so we're going to have a hard stop a few minutes before 1:30, and that means that we should all try to get out in an orderly way, and in particular, if you have any cups or plates or other things with you, please take them out with you and don't leave them behind. All right, thank you. Okay, so also in the interest of time, I'll try to keep my introduction slightly more brief than usual. I apologize, Michael. Michael Bender is a professor emeritus of Geosciences. He is a geochemist who measures concentrations and various isotopic signatures of important chemicals across a range of environments, from oceans to atmospheres to sediments to ice cores. He's well known for his work in all of those, probably best known for his work on measurement of trapped gases in ice cores, which have given us remarkable insights and information about geological history of the planet. As you will see, he's also been involved, along with other Princeton colleagues and other collaborators, in recently retrieving by far the oldest ice core that has so far been retrieved, well over 2.5 million years old, and he'll be telling us something about that. Michael has received a number of awards, including the Patterson Medal from the Geochemical Society, the Revell Medal from the AGU, the American Geophysical Union, and he's a member of the National Academy of Sciences. He's also a fantastic colleague, and please join me in welcoming Michael Bender.
Thanks for the invitation and kind introduction. Thank you all for coming. Okay, so this slide summarizes the talk. I'm going to give you some background information about archives that are used in climate history, both from deep sea sediments and from ice cores. And I'll also talk in the context of background of the role of Earth's changing orbit around the sun in pacing and causing glacial or glacial climate change. I'll show you characteristics of Earth's climate over the last 2.7 million years. Then I'll show you new data that Mike referred to, characterizing greenhouse gases and other climate properties before 800,000 years ago, when the ice core record, the existing ice core record runs out. And finally, I'll end with a hypothesis that attempts to explain a large change in the nature of glacial and interglacial cycles about 1 million years ago. So there are two important climate archives that I'll talk about in this talk. The first is deep sea sediments, and the second is ice cores. In terms of deep sea sediments, the most important single property that's measured is the ratio of oxygen 18 to oxygen 16 in the calcium carbonate of microfossils that lived on the seafloor. This is an example of the fossils in which this measurement is made. This is a single-celled organism that lives on the seafloor, secretes a skeleton of calcium carbonate. And the property of interest is the ratio of oxygen 18 to oxygen 16 in the oxygen atoms of this calcium carbonate. Both of these isotopes are oxygen. They have virtually the same chemistry, but their mass is a little different. And this difference in mass causes subtle differences in their chemical and physical properties, which turn out to be hugely interesting in paleoclimate. So higher values of this ratio, the ratio of oxygen 18 to oxygen 16, reflect two climate properties. The first is the greater extent of ice sheets on the continents, more glaciers. And the second is the temperature bottom water in which this calcium carbonate was precipitated. And that's interesting, partly because bottom water temperature is important, but also this is the bottom of the ocean. This is the surface at high latitudes. The temperature of the surface at high latitudes is about the same as the bottom water temperature of the oceans. And so this property, which is expressed as delta O18, higher delta O18 means higher ratio of oxygen to 18 to oxygen 16, means more continental ice and colder temperature. Separating those two is hard, but the conflated property is very interesting. And then the other archive I'll be talking about, of course, is ice cores. This shows a driller extracting ice cores from a drill tube. This is a picture of a person holding an ice core sample. You can see bubbles of air in this ice, which preserve ancient atmosphere and give us a window into the chemistry of past atmospheres. The other property that's of interest here is the ratio of deuterium to hydrogen in the water. Hydrogen is one isotope of hydrogen, just a proton. Deuterium is another isotope that's a proton and a neutron. And again, the ratio of the heavy isotope deuterium to hydrogen reflects a climate property. In this case, it's regional temperature. And higher values of the D to H ratio is expressed as delta D, and higher values indicate warmer regional temperatures. I should say that the use of these isotopes may seem like magic if you haven't thought about it, but in practice, there's a solid theoretical foundation behind this use, and there's loads of empirical data that back up the use of these proxies, as I've described. Okay, I said that Earth's orbit around the sun changes with time, and those changes have an impact on glacial or glacial cycles. There are a number of facets to that topic, and I'm just going to discuss one of them. In this diagram, here's the sun, here's the Earth. The Earth's spin axis is tilted, and the hemisphere that's tilted towards the sun is having its summer. So in this diagram, the northern hemisphere is having its summer, southern hemisphere is having winter. In half a year, the Earth will move around the sun and it'll be over here, and at that point, southern hemisphere will be pointing towards the sun having its summer, and northern hemisphere will be having its winter. If there were no tilt to the spin axis, then no seasons, big tilt, big seasons. In practice, the tilt varies from about 21 degrees to 24 degrees over a period of 40,000 years. So there's a 40,000 year period over which Earth goes from having extreme seasons, warm summers and cold winters, to more moderate seasons, intermediate summers, intermediate winters. The role of this process in the ice ages comes from the idea that goes back to Milankovitch, comes from the idea that the key thing in growing an ice sheet is to preserve the snow and ice to preserve the snow and ice across the summer. So if you have cool summers, then snow and ice will be preserved, and there will be additional accumulation during the following winter. Then that snow and ice will be preserved through the following summer, and so on. If you have warm summers, then you melt all the snow and ice that accumulated during the winter, and you can't build an ice sheet. So high tilt leads to warm summers, the decay of ice sheets. Low tilt leads to cool summers and the growth of ice sheets. And as I said, the cycle of that process is 40 of that change is 40,000 years. Are there any questions at this point? Okay, so this is a plot. of the delta O18 of these benthic seafloor dwelling forearms, the delta O18 increasing in this direction versus time in the past. And time goes from 0 to 65 million years ago. So down is colder, more ice. And what you can see in this slide is that at least for the last 50 million years, there's been a progressive cooling to the point where about 2.7 million years ago, northern hemisphere glaciers began to make a mark. By northern hemisphere glaciers, what that kind of means is that the glaciers got big enough to come down to the shoreline and calve into the ocean. And I'm going to be talking about these last 3 million years. On the next slide, I'm going to show you a blow-up of this plot in which I stretch out the last 3 million years of the record all the way across. And what you'll see is that a lot of what looks like noise here is in fact signal. So this is that record, and there are a number of things that I want to point out. First, just to orient you, time goes from, age goes from 0 today to 3,000 years ago. The age units here are in thousands of years. So this is 3 million, 2 million, 1 million years ago. The delta O18 is plotted of the calcium carbonate is plotted on this axis. Higher is downward, so downward is colder and more ice. And then this is a climate record that was obtained by averaging records from a lot of individual deep sea sediment cores. And there are a number of things I'd like to point out about this plot. First of all, you can see that there's been, on average, a progressive cooling of Earth's temperature over the past 3 million years. Second, you can see that climate is never static, as our global warming skeptic friends tell us. In fact, it's always dynamic. The climate cycles here are shorter than the climate cycles here. In fact, these last about 40,000 years on average, and you would be correct if you connect that with the period of change in Earth's spin axis. And then for the last 800,000 years or so, we're in the world of 100,000-year climate cycles. The 40,000-year climate cycles are of smaller magnitude than 100,000-year climate cycles. And finally, the interglacial conditions, you can see, don't change very much. There's variability, but there's no long-term trend. Whereas the glacial conditions are such that the ice ages are much colder during the last 800,000 years than during earlier times. This world of 40,000-year climate cycles called the 40K world. This part is called the 100K world. And the transition from one to another is the mid-Pleistocene transition. So what I want to do next is say something about what the nature of the glacial cycles was during the 100,000-year world. For example, 20,000 years ago, Earth was in the pits of the last ice age. What was the environment like at that time? So global temperatures were about 6 degrees colder, more colder in high latitudes, a little less colder in the tropics. Glaciers covered North America almost to the latitude of Princeton. Also Scandinavia, British Isles, other parts of Northern Europe. And there was no ice in Siberia, but north of Siberia there was a huge glacier that was grounded on shallow seafloor in what's now the Arctic Ocean. All this, the water making up this ice had to come from somewhere. It came from the oceans. So as the ice sheets got higher, the oceans got lower. And in fact, there was a sea level lowering of about 135 meters. The concentration of carbon dioxide during the last ice age was lowered by about 40%. And concentrations of other greenhouse gases were also lower. And there were a lot of shifts in precipitation, and the planet was somewhat more arid during the ice ages. This slide shows climate records of the 100K world. So on this slide, time goes from age goes from 0 to 800,000 years ago. Time goes in this direction towards the present. And then shown here are different climate properties. This is the Dodo 18 of benthic forams, which is the same property that we've been looking at. Here stretched out again to 800,000 years full scale. This is delta D, which is a measure of the temperature in East Antarctica, where an ice core was maintained. It went back to 800,000 years. CO2 concentration, methane concentration, and this is dust. And I just want to point out two things with regard to dust. Dust is plotted increasing downward, and it's a natural log scale, so the entire amplitude here is about a factor of 400. And what you can see is that all these properties change more or less in lockstep during the 100K world. So when you had warm conditions in terms of high latitude temperatures and ice volume, Antarctica was warm, CO2 concentration was high, methane was high, dust was low, and when you had cold climates, everything was reversed. Antarctica was cold, CO2 was low, methane was low, and the dust concentration showed by these glacial values, the dust concentration showed by these glacial values down here was very high. So, this record ends at 800,000 years, and the reason is that that is the age of the oldest continuous ice core record that we have. And so the properties like Antarctic dust, temperature, and greenhouse gases, we don't have any primary information on those right now beyond 800,000 years. But there's a lot of interest in extending records like this back to the mid-Pleistocene transition in the 40K world. So, in fact, there are groups in the United States, in Europe, and in China that are thinking about how to extend back these records. And there are two approaches that people envision. The first approach is you just go to some place where there's a normal glacier flowing calmly towards the oceans. And if you stand here on top of the glacier and look down, below you there's ice there are layers of ice that are older and older and older. And as you go deeper, you get older. So one thing you could do is identify such an area with a simple glacial stratigraphy that goes back to 1.5 million years instead of 800,000 years, drill an ice core through that glacier, and get a continuous climate record extending back into the 40K world. And hopefully that will happen sometime sooner rather than later. But right now there are two big problems. First of all, nobody knows where you might drill and find a record that goes back continuously 1.5 million years. And secondly, failure is extremely expensive because drilling through 3 kilometers of ice is a logistically very complicated process that costs many tens of millions of dollars. The second approach, and the one that we've worked on, is to go to some place where the glacier is flowing to the ocean, but instead of calving into the ocean, it hits a mountain. And then its flow, instead of going like this, carries it up like this. And if you're lucky, you might have relatively warm, dry winds at the surface, which continuously evaporate the ice that's coming up. And so in that case, the ice here is going to be young, older, older, older. And then as you go over here, it'll be young at the surface, older, older, older. And what you want to do is sample ice in the area of the mountain where presumably the oldest ice is to be found. So we've been part of a collaboration to do this. The project that I'm going to talk about has been led by my colleague John Higgins. Eugene Yan is a student working with us. There have been a lot of other people involved, all of whom have played critical roles because of their expertise and resources. But I just want to mention one name in particular, and that's Paul Majewski, who's a professor at the University of Maine, who first conceived this project and who chose the site where we were going to drill and prospect for old ice. This slide shows the field area. The black square here is the general area. It's north of McMurdo, pretty close to the coast of the Ross Sea. This black square blown up is shown here, and black is non-attacks, the tops of mountains that stand proud of the ice, and white is ice and snow. And then this square here, which is the area where we work, is blown up into this figure. What you see, when you see white here, that's snow. The blue areas are old ice that has come to the surface that take on a blue color for optical reasons. And there are two areas in here where we've worked. The first is along this line here, which represents a flowing glacier, smoothly flowing glacier without much turbulence, so it maintains stratigraphic continuity that is flowing through a gap in the mountains. And this area turns out to be important for our studies. We've gotten ice there ranging in age from 100 to 250,000 years old, measured its properties, and that gives us a reference for ice from the 100,000-year world into which we can fit our observations of older ice. And then this area over here is an area with mountains blocking the flow of the glacier, and so the ice is just kind of stuck there, and there's a possibility of obtaining very old ice in this region. I didn't participate on the field season. I'll show you some of John's pictures. This is the tent in which the ice drill was placed. I should say that the capability of the drill that we used is to go down to about 200 meters, maybe a little deeper than that. And it's logistically far simpler than drills intended to go down 10 times as deep. Anyway, this is the drill tent. This is the inside of the drill tent. Part of the drill that's lowered down into this hole and spun around until the cutters cut a core of ice, which is then retrieved. This is the field camp. These are, excuse me. Yeah, this is the field camp. These are tents where people lived and slept and ate. There was a storm during the season, and the drill tent got done in. The team got out the shovels and shoveled away the snow and resurrected it, and the work went on. And finally, this is a picture of Eugene with what I think is the deepest sample from the last core that was drilled. Right, Eugene? Okay, so in this diagram, we're working in an area where ice flowing hits the mountains and comes up to the surface. We can sample in three different ways. One is just to walk along the surface from younger ice to older ice and whack out bits of ice as you go along, and so we have an age sequence from younger to older. The second thing is to sample in this stratigraphically simple region away from the bedrock and get a vertical ice core. And then the third thing is to get a vertical ice core in a region close to the bedrock. And the hope here, first of all, this is the region where the oldest ice is going to be. But in addition to that, the hope is that some of this, that ice in contact with the bedrock is frozen to the bedrock, and it's going to be immobilized and stay around for long times. And then the downside to repeat is that this ice is highly unlikely to be stratigraphically continuous. So what you're doing is working with chunks of ice, each of which has its own personal age and characteristics. When the ice comes back, the first thing that you do is date it. And the way we've done that is to measure its argon concentration. The idea is that potassium in the Earth is radioactive. It decays to argon. Argon is a gas, leaks out to the atmosphere. And so with time, the amount of argon-40 in the atmosphere gets higher and higher and higher. And so we measure the concentration of argon-40. The lower it is, the older the ice is. There's more to it than that, but that's the essence of it. This is a plot of age versus depth in the two cores we drilled in this area close to the bedrock high, hoping to find old ice. So on this plot, depth goes from 0 to 200 meters, and age goes from 0 to 3 million years. In the first core, 1502, we obtained ages of about 500,000 years down to about 180 meters depth. This age is not interesting because we have ice of this age in continuous records from the deep Antarctic ice cores that I showed you before. But then in the bottom 15 meters or so, we dated 6 samples, and 3 of them are relatively young and not of great interest. And then 3 of them are range in age from about 1.2 million years to 2.3 million years. So there's some ice in this interval that dates back to the 40K world, and that's of great interest for our objectives. And then this is the other core. Here the ice is about 300,000 years old, down to about 125 meters depth. Then there's a layer of ice that's about 1 million years old. It dates to the mid-Pleistocene transition. And then in the deepest part of the core, we dated 7 samples, 6 of which date from 1.3 million years to 2.7 million years and come from the 40K world. And so now we have old ice, and we can start investigating climate properties of the 40K world. Now, the uncertainties in these numbers are pretty large, and so we can't link individual ice samples with individual glacial events. And the way we've treated this data is to divide it into 2 groups. First of all, 3 groups. First of all, everything that's younger than about 900,000 years gets excluded. Secondly, million-year-old ice we've lumped together as mid-Pleistocene transition ice, and anything older than 1.2 million years is from the 40K world. And we're going to compare the mid-Pleistocene transition 40K world ice with ice of the 100K world. So these are the 100K records I've showed you before. This is the delta 18 of the forams from deep sea sediments. It goes from 0 to almost 3 million years ago. Same record you saw before, except that there's a scale change here, and everything before 800,000 years is highly compressed. And then this is CO2. And this is delta D, which is regional temperature, and finally methane. So what do we see? First of all, looking at regional temperature, the warmest temperatures from the mid-Pleistocene transition ice and 40K world ice fall within the range of the warmest temperatures of the last 800,000 years. The same is, but the coldest temperatures do not get anywhere near as cold as the coldest temperatures of the last 800,000 years. CO2 is the same. The highest CO2 values from the mid-Pleistocene transition, the 40K world, are in the range of values of the last 800,000 years, but the lowest CO2 values do not fall as low as the lowest glacial values of the last 800,000 years. Methane, the picture is interesting and a little more complicated. And then for delta D, the picture is the same as what I just said for temperature, Antarctic temperature, and CO2. The glacial values of the 40K world, say from here to back to here, the interglacial values of the delta 1804 Ms fall within the range of values of the last 800,000 years. So all these interglacials, I wouldn't say they were equivalent, but there's no systematic trend in how warm or how cold the interglacials were. Whereas the glacials get progressively colder, and values during the last 800,000 years are significantly colder than the 40K world. Antarctic temperatures of the last 800,000 years are colder than the 40K world, and CO2 values of glacial samples of the last 800,000 years are lower than values of the 40K world. So climate change seems to have been a reversion during every interglacial period to about the same conditions, and then glacial periods that have gotten progressively colder, or in step fashion gotten colder across the mid-Pleistocene transition. This is a plot of CO2 concentration on the y-axis versus regional temperature, or East Antarctic temperature, on the x-axis. Higher delta D values imply colder regional temperatures, colder Antarctic temperatures, and these values are in fact increasing in this direction, go from more negative to less negative, so warming in this direction. The gray points represent CO2 versus Antarctic temperature during the 100,000 year world that prevailed for the last 800,000 years. The yellow points represent CO2 versus East Antarctic temperature during the mid-Pleistocene transition. The red points represent CO2 versus temperature during the 40K world. And you can see that, that the relationships are similar for all these times. And what distinguishes the 100K world, which falls uniquely down here, is the absence of low CO2 cold ice during the 40K world, and its presence of low CO2 cold ice during the glacials of the last 800,000 years. And I also wanted to say that in the mid-Pleistocene transition data and 40K world data, there's a statistically significant correlation between CO2 and temperature, Antarctic temperature. And so this is a little bit more evidence for CO2 climate link in glacial or glacial cycles. Okay, what I'd like to do finally is end up discussing a hypothesis about this transition from 40,000 year climate cycles with relatively warm glacials or less cold glacials to 100,000 year climate cycles with very cold glacial conditions. So this is a series of events that represents the hypothesis. And I want to start with the idea that mountain glaciers in the southern Andes between about 46 and 55 degrees have been periodically glaciated during the last couple million years. We don't know they've undergone glacial and interglacial cycles. What happens is there's always a core of mountain glaciers at the highest elevations. During glacial times, this core solidifies and it extends down to lower elevation and becomes a large ice sheet in the Andes. And then during interglacial times, it retreats back to its refugia at high elevations. The intensity of Andean glaciation increased until about 1 million years ago, when it reached its maximum in an event called the Great Patagonia Glaciation. These glacial events tended to grind up the bedrock into fine particles and to create cold, dry areas with these fine particles where winds could entrain the dust and sweep it up into the atmosphere and carry it out over the Southern Ocean. Once the dust gets to the Southern Ocean, some of the iron in the dust dissolves in the water. And this dissolved iron then becomes available to phytoplankton, which are starved for iron in much of the Southern Ocean. Phytoplankton grow more rapidly. They assimilate CO2 and make it into organic matter. That organic matter sinks down, bringing carbon to the deep ocean and leaving the surface ocean impoverished in inorganic carbon. Because of air-sea equilibrium, CO2 in the atmosphere then diffuses into the surface ocean to replace this CO2 that's been drawn down, and the concentration of CO2 in the atmosphere decreases. And so the suggestion is that this is what's happened to induce CO2 changes, that this process first became active about 1 million years ago during the mid-Pleistocene transition. Before 1.2 million years ago, there were other processes that led to variations in CO2, but the difference is that across the mid-Pleistocene transition, this extra process associated with Patagonian dust came into play, further lowering CO2 concentration during glacial times. So CO2 after the mid-Pleistocene transition is lower during glacial periods than during the 40K world. Colder glacials leads to colder temperatures, bigger, more stable ice sheets, and more inertia in the climate system, which plausibly leads to longer glacial interglacial cycles. And this last thing, linking more intense glaciations with longer cycles, so as a mechanism to go from the 40K world to the 100K world, this is all speculative, but that's more speculative than a lot of the rest of this. So let's look at some evidence for this. The first comes from a paper involving Danny Sigmund, and first authored by Martinez Garcia, showing evidence for increased dust flux across the mid-Pleistocene transition. So what's plotted here on the x-axis is age, millions of years before present, going back to 4 million years. The mid-Pleistocene transition was about 1 million years ago. And this is the dust accumulation rate in the deep sea sediment core from the Southern Ocean. And what you can see here is, it's not clear what the maxima and minima correspond to, but it turns out that all these maxima correspond to glacial periods, all the minima correspond to interglacial periods. So what you see here is an increase in the dust flux to the Southern Ocean during glacial periods as recorded in deep sea sediments. And that would lead to an increase in the dissolved iron concentration, increase in phytoplankton growth, in carbon export, and an uptake of CO2 from the atmosphere. You may wonder why this focus on Patagonia and the Southern Ocean. As Jorge and Danny Sigmund, Robbie Todweiler, maybe other people here have shown, the Southern Ocean is a place where you can remove iron really efficiently if ecosystems are iron. The way you can remove, the Southern Ocean is a place where you can remove carbon really efficiently partly because of high nutrient concentration. So if you want to add iron to someplace in the oceans and get the biggest bang for your buck in terms of carbon removal, the Southern Ocean is the place to do it. So in addition to this, there's modeling evidence linking Southern Ocean dust to Patagonia. Patagonia is the main source of dust to the Southern Ocean, although Australia and South Africa contribute some. There's biogeochemical evidence, a lot of it, for enhanced productivity when iron is added to ocean ecosystems. And as I've shown you, there's ice core evidence for a decrease in the glacial CO2 concentration as you go from the 40K world to the 100K world. To summarize, I've shown you, I talked to you a little bit about climate archives and climate proxies based on deep sea sediments and ice cores. I showed you evidence that there was a big change in the period of glaciation going from 40 to 100,000 years and the intensity of glacial periods about 1 million years ago. I've shown you our new data for the CO2 change and the temperature variations in Antarctica during warm and cold periods of the 40K world and 100K world. And I've suggested a simple hypothesis. Actually, I've cobbled together various views in the literature to make a simple hypothesis about the cause of the transition in climate patterns between 40K world to 4 million years ago and the 100K world after. Thank you.
We have time for questions, so please.
Can you explain what caused what in this sequence? You had, why was there lower CO2 causing the dust, causing the floods, or could things have been reversed, that there was the dust and that? What was the order of things and what caused what?
Oh, yeah. The question is, what was it? The question is, how well do we know the sequence of events that, according to this hypothesis, led to this sequence of changes? So something caused CO2 to change. And what I'm saying was it was the extent of glaciation in Patagonia. And so then you might worry about whether CO2 was changing before or after the coldest episodes of the glacial period that I'm saying are enhanced by Patagonia dust. And the way I think about this is CO2, to a first approximation, CO2 and global climate track each other pretty well. So maybe CO2 started changing first. For example, it started decreasing, and global temperature started decreasing because CO2 decreased. And that fits the picture I've given you. But the other possibility is that the Earth started warming first, and that led to the CO2 decrease. And so their CO2 is responding to climate. When CO2 decreases, that will lead to a cooling. And so whether CO2 is the first property to decrease or the last property to decrease, it's still going to contribute to colder climates. And so for the specific mechanisms of climate change, it's really important to look at high resolution in the sequence of events that you referred to. In terms of the broad picture of climate change, CO2 is going to have its influence one way or another.
This is really a follow-on to the question that was asked. You discussed a very interesting feedback system that feeds on itself until it stops. And the question is, what brings it to a stop? Is it the change in the tilt of the Earth or some other mechanism that brings glaciation to a halt?
Okay, I hope everybody heard that. Does anybody want me to repeat the question? To repeat? Yeah, okay, so in the 40K world, you have warm periods and that are up here and cold periods that are down here. 100K world, warm periods are about the same place, cold periods are here. Why do you keep going back and forth between these same limits? So my guess is that at the warm end, so let me go back a minute. A very important aspect of glacial or glacial climate change is the so-called ice albedo feedback. During glacial periods, large part of the Earth is covered with ice sheets which reflect sun's heat. And so the melting of ice sheets itself or the growth of ice sheets has a large impact on climate. I think what happens in an interglacial time is basically you melt all the ice sheets on North America and Eurasia, and probably whatever ice there is in Patagonia. And then if you want to keep going, and that's the stage we're at now, if you want to keep going, the next thing you do is to melt Greenland and to melt the West Antarctic ice sheet. And that would give you another 14 meters of sea level rise. But it would not give you a huge impact on climate, partly because those areas are so far north, they don't see much sunlight to reflect. So Earth just can't get hot enough to completely melt the Greenland ice sheet and the West Antarctic ice sheet and then parts of East Antarctica. Just can't warm up enough to do that. And then on the glacial side, for the last 100,000 years, seems what happens, this is a hypothesis of Maureen Ramos, seems what happens is that the ice sheets grow and grow and grow until somehow their size becomes destabilizing. And at that point, they become unstable. And people have suggested specifics for this process. They become unstable, can't sustain themselves any longer, and they rapidly melt, and you have the deglaciation. So that's how kind of I understand these limits.
Yes, there are a lot of different hypotheses for the mid-Pleistocene transition between the 40,000 year and the 100,000 year cycle. Is there any sort of observation that would be like a smoking gun for the Patagonian dust hypothesis as opposed to the various competitors?
So what are the competitors? One is that the nature of North American glaciation, which is the largest ice age glacier, the nature of North American glaciation essentially changed progressively as one glacier after another slid over the continents and essentially moved dust.
The soft sediment off that was sitting on Antarctica.
Right. What other ones?
That's the biggest one.
Okay. Okay. So so a competing hypothesis is the one I talked about with Patagonian dust and CO2. That one makes predictions that can be tested, which I think which makes me like it. But I don't think we can eliminate the so-called regolith hypothesis.
Is there any evidence for increased phosphate in the ocean at the same time as an increase in I deposition?
Not that I know of on these time scales. The question was, is there evidence for an increase in phosphate in the oceans? I'd say not that I know of on these time scales.
Can you tell us more about the changing tilt of the Earth's rotation between 21 and 24? What's causing it, and where are we now, and what direction are we headed?
Yeah, so this is somewhat of an embarrassing question. It has to do with the gravitational pull. The changes in Earth's orbit have to do with the gravitational pull of the moon and the other planets. Tilt in particular, John, do you remember? Anybody? Can anybody? Okay, I'm not sure, but anyway, it's the gravitational pull of the other bodies in the solar system.
Well, it's also, I believe, the Earth is rotating on its axis and it wobbles like a top. And eventually, from what I've read and heard over the years, it's eventually going to flip in the other direction. I mean, it's tilted in one direction now, but with this wobbling through time, it's going to eventually shift over.
Yeah, so I spent hours and hours shortening my talk. That was one of the things I felt like I just had to pick out. And I'm sorry, but maybe we could do other questions instead of...
Maybe two more quick questions, and then conscious of time.
Is there any link between your discussion of dust and when we're asked to think about the role of aerosols in modern climate systems?
I think there is, because some people have made the argument that that particles were adding to the... So the question is there a link between dust and aerosols that we're adding to the climate system? First of all, aerosols we're adding to the climate system tend to reflect sunlight back to space, and people have looked at glacial dust levels in that same heat balance context. And secondly, there are probably nearshore areas that are being impacted by particles entering and iron, but it's unlikely to be a major thing, because if you, aerosol iron would have an impact near the sources, which is, say, coastal waters. And they already have shallow seafloors that can provide lots of iron. And one
more quick question, perhaps.
You mentioned the molecular cycles as potentially being involved in the 40K cycles. Wouldn't there also be essentially a ringing at that period in the 100K, in particular for the melting?
Yeah.
Give a 30-second
Henry asked about, said, as I understood, that the 40K cycles must continue into the 100K world. And that's true, and you can see that periodicity, but other things are coming into play.